Hey everybody, it's Bruce and the dog on the floor, and today we're going to be talking about Julia's FluxML, a machine learning library. And we're specifically going to be talking about activation functions and why you might need them in a machine learning problem. So let's go ahead and get started. We're going to spend most of our time in the Julia console, so let's open that up and get going. We're actually going to be running this from the Julia console. And the reason I want to be able to control precisely when the training steps get called, because I'm going to actually do some things around activations. And I want to make sure that you get the point that there are some situations where activation functions can help things converge or even let them converge at all. So we're going to be solving a problem around Boolean logic. And so you might have seen that true and true, that's going to give you true, or true or true. That's also going to give you true, like a true and false is going to give you false. Well, in Julia, you can also use ones and zeros for Boolean operations. So for example, 1 and 0 is going to give you 0 because 0 is the analog for false, right? And so the one that we're going to be doing is XOR. And so 1, and so the same number will always give you false. The only way that this could be true, this is exclusively OR, which means that the first one or the second one is true and the other one is false, right? So both of these have to be different. And the reason that this is interesting to us is that there's not a linear progression through them that Julia can learn. And so we're not going to be able to build a model without activation functions that can simply work, right? So here's what I mean. So let's go ahead and build the data. So let's say the X terrain. So these are essentially all the possible values that I can have of ones and zeros. So I'm going to say 0, 0, 1, 1. And this is the first input or the first feature. The second feature, I want to have all possible combinations. So I'm going to say 0, 1, 0, 1, right? So that gives me 0 and 0, 0 and 1, 1 and 0, and 1 and 1, right? And so this is going to give us a matrix where every column is an observation and every row is a feature. So it's essentially, this is the first argument and the second argument for our feature. And the rows is 0, X or 0, right? So what are those answers? So it should be false for this first column, true for the second, true for the third, and false for the fourth, right? False when they're the same, true when they're different. So I'm going to say that Y train is equal to, and I'm just, rather than building the XOR function, I'm just going to say 0, 1, 1, 0, just to do this by hand. And so you could actually call the XOR function if you wanted to build this out. I don't think we need to do that. But let's go ahead and build a model. So this first model, so essentially we want to produce a 1 or a 0 at the end. And that's the thing that we want to learn. So it's going to have, and it's going to have two inputs. But what I'd like to do is do two dense layers. Where the number of inputs of the whole thing is 2, the number of outputs of the whole thing is 1. And just to keep things simple, let's just have a hidden layer that's a size of 2. And we're not going to use an activation here. So this is effectively going to be the identity. Remember, the identity layer is like having no activation function at all. It just means return whatever the result of this function is. So, and we're going to chain these together. Okay, so did I do a using Flux? Probably not. So let's go ahead and fire this up, and then I'll be able to create my model. So we'll let this run, and then we're going to create the model. Okay, so now we have a model, we have the data. Let's go ahead and shape the data the way that Flux likes it. And so this is going to be X train and Y train, like that. And so that's the data. So I need the parameters. So the identity parameters are going to be params of the model. And actually, I think I want to, later I'm going to label the other one the sigmoid model. So I'm going to label two loss functions. One is the identity loss, and identity labeling the sigmoid function, right? Which is, this is going to be x and y, and all it's going to be is the flux dot loss, or the losses dot MSE for mean squared error. And we want to take the x, but we're going to build a prediction. So how do I do that? I do that with the model. And then I want to compare that against the actual values. And this is going to be x and y, the ones that come from here. And we're going to pass, eventually we're going to pass train x and train y through for those. That's great. Perfect. So to do a flux, if I want to do a flux.train, so this is going to take a loss function. We have that. It's going to take parameters. We have that. We need data, but we're also going to need an optimizer. So let's say that the optimizer is equal flux dot optimize dot. So I want to grab the one for gradient descent. That's the one we've been using so far. It's basically the one that they teach you in school. It's the first one that you learn. And it's going to pick a default learning rate of 0.1, which is fine. And so now we have everything that we need to train this model. So let's go ahead and see. So what is the loss for this thing? Loss for the model. So the loss, and we're going to pass it x. This is the identity loss. And we're going to pass this x train and y train. Okay, so this loss is 1.2. We ought to be able to do better than that, but let's go ahead and train this thing. So train, and so what do we need? We need the identity loss, and we need the parameters that we built. So that's the identity parameters. And then we need the data and the optimizer, right? And so we're going to run this a couple times. So we're going to say for epoch in, let's say 1 to 5,000. You know, since this isn't going to take long to run after the initial complication, let's hit it pretty hard. We need to do the flux train. Okay, and then let's see how close that we can get. So it's not really taking long to train this thing. It's actually taking a long time to pre-compile it. So we ought to be able to run through that again, but I want to pick up a second version of the loss, right? So the first version of the loss was right. So there's the identity loss. It's right here. And so we ran the identity loss and we came up with a 1.2. And let's see if we get, so the losses come down, but let's go ahead and run that training again and let's check the loss. So that loss is still there. Let's go ahead and see what our predictions look like. So the model of the X train. So remember, this should give us false, true, true, and false. So something close to 0, 1, 1, and 0. Let's see if we get that. So it doesn't look like this is training very well. So I wonder what's going on. So let's go ahead and run this again. Maybe we're not training enough. So let's go ahead and run this for a good long while. So we'll run 50,000 of them and see if we don't converge a little bit better. Okay. Okay, it's not converging, right? And so we can verify that the loss is not getting much better. In fact, it's not getting any better at all, right? And what's happening is that this model, So let's pull up the model again. So there's the identity loss, and here's the model. So the model is right here, right? And this is a linear function. Remember, sorry about that. So this is a linear function. This is wx plus b, and essentially doing two versions of that with multidimensional data. But what I really need here is an activation function. So I'm going to add an activation function, and I'm going to relabel this. I'm going to call this the sigmoid model, or maybe, yeah, I think that's fine. The sigmoid model. So we're going to need another loss function. So let's see what Flux train needs again. So it's going to need a loss function, and we're going to have to pick a different loss function, right? Because now we have a different model. We have the parameters, and the parameters are going to be different again because it's a different model. The data is the same, and the optimizer, this particular optimizer doesn't carry state with it. So, or it doesn't mutate state with it. So we can continue to use that one, but just for grants, we can build another one. In case my understanding is incomplete there, but we do need to build another loss function. Let's call this a sigmoid loss. And I mean this from the perspective of this is the loss for our sigmoid model, right? So I want to call the sigmoid model, right? Meaning the one with the activation function in it of x, sigmoid loss of x and y is equal to the flux.losses.msc, and this is going to take the sigmoid model of x and y. So now I have a new loss function. I need the sigmoid model p's is equal to params, the params for that sigmoid model. So now I've got those, and now I can go ahead and take a shot at the optimizer. So I'm going to say, so we're going to pick up this loop again. Let's shorten that a little bit just to kind of see where things start to converge for us. But we're going to need that sigmoid loss, and this is the sigmoid parameters. And the data is the same, the optimizer is the same. So let's go ahead and let that fly. And now let's type sigmoid loss of the x train and y train. Okay, so this has already come down. So I bet if we predict, and this is just with 5,000 here. So I bet if we ran a prediction, sigmoid model, and we were going to pass it the x train data. Let's see what we come up with. So this is a 0, 1, 1, 0. So this one's pretty close. But if we really push this training out like we did the last one, we're going to get something that comes where this is really going to converge nicely for us. And then we can check the loss to be sure. Yeah, you can see that the loss is way down now. And now I can actually run the model. Yeah, and this is very close to 0. This is very close to 1, 1, and 0. So effectively what's happening is the sigmoid function is an activation function. It's allowing us to do two things. The first is it's letting us make nonlinear predictions. And second, it is improving our convergence. And that's really exactly what you want out of the sigmoid function. You want to be able to build models that converge quickly and can predict complex data. And that's an excellent thing. From Bruce and the dog on the floor, it's Croxio Learning.